Hello and welcome back to another deep dive. I want to start today by taking you out of the classroom for a minute.
Yeah.
Imagine you're walking past the biology lab in your school. The door is slightly open, and suddenly you get hit with that very specific sharp smell. You know the one I mean, right?
Oh, absolutely. That stinging smell that sort of hits the back of your throat, it's unmistakable.
Exactly. It's pungent, it's sharp, and it feels like it stays in your nose for hours. That's formaldehyde.
Right.
Or think about this, sitting in a room when someone opens a bottle of nail polish remover. Even if you're sitting, 10 feet away, you smell it almost instantly.
And if you leave the cap off that bottle,
Uh-huh.
the liquid it disappears. It evaporates so
This
fast.
flies into the air. But here's the question I've always had. Why? Why do these liquids smell so strong? And why are they so eager to escape the bottle? Is it just random or is there a reason for it?
It's definitely not random. And it's
Right.
not magic either. The secret lies in a very specific chemical bond, a bond that acts almost like a magnet.
A magnet. Okay, now I'm curious. So, what are we diving into today?
Today, we are cracking the code on the nomenclature and structure of the carbonyl group.
Ah,
This is the foundation of Unit 8, aldehydes, ketones, and carboxylic acids.
Unit 8. Okay. I know a lot of Class 12 students get a bit nervous about this unit because it's huge. It carries a lot of marks in the board exam.
It is a heavyweight unit, yes. But here's the good news. Today, we're focusing strictly on the structure itself. And if you understand this one structure, this carbonyl group, you basically unlock the master key for the entire chapter.
The master key. I like how that sounds. So are you saying that if I get the structure right, I don't have to purely memorize all those reactions later on?
Precisely. If you understand the carbonyl group, this C-double bond-O structure, you'll understand why aldehydes and ketones behave the way they do.
Okay.
You won't just be memorizing equations, you'll be predicting them. You'll know why they undergo nucleophilic addition, and you'll know exactly how to name them.
Okay, that's a big promise. Understanding the why makes the what much easier to remember.
So let's unpack this. Let's start at the very, very beginning. At the simplest level, what exactly is a carbonyl group?
At the zero level, the simplest explanation is this. A carbonyl group is just a carbon atom double bonded to an oxygen atom. In your notebook, you'd write it as C, then an equal sign, then OCO.
C-double bond-O. Okay, that sounds simple enough, but I
Yeah.
feel like there's more to it than just, drawing two lines.
Oh, there is much more. We need to look at what's really happening between those atoms.
Right, because usually when I think of a double bond, like back in class 11 with alkenes, I think of equal sharing. Two friends holding hands equally. Is that what's happening here?
Not at all. And this is the most critical point. Imagine carbon and oxygen are holding hands, yes. But oxygen is greedy.
Greedy. In what way? In chemical terms, we say oxygen is highly electronegative. Think of it like a tug of war. Oxygen is much, much stronger than carbon. So even though they're sharing these electrons in the double bond, oxygen is pulling really hard. It's hogging the electron blanket, so to speak.
So poor carbon is left shivering without the blanket.
Exactly. Because oxygen pulls the electrons closer to itself, it creates what we call a dipole.
A dipole.
The oxygen becomes slightly negative. We write that as delta minus.
Right, delta.
And the carbon, because it's losing that electron density, becomes slightly positive or delta plus.
Okay, I want to make sure I have this right. So we have a double bond. One atom, the oxygen, is hoarding the electrons, becoming negative. The other atom, the carbon, is left feeling positive and, well, empty.
You got it. And to get a bit technical for just a second, remember that a double bond consists of one sigma bond and one pi bond.
Yes, sigma and pi. I remember that.
The sigma bond is strong, it's stable. But that pi bond, that's where the electrons are more loosely held. That's the cloud that oxygen is distorting.
Ah, so the pi bond is the one in the tug of war.
That's the one, and that's what makes this whole group so reactive.
Okay, that makes sense. But before we go further, I have a confusion that I think a lot of students have. When I see CO, my brain immediately goes to acids, like acetic acid. Is that the same thing?
I am so glad you asked that. This is the classic misunderstanding trigger. We need to fix this right now before the exam.
Please clarify. What is the difference between a carbonyl group and a carboxyl group? They sound so similar.
Listen carefully. The carbonyl group is strictly the CO part. Just that. This is what you find in aldehydes and ketones.
Just CO. Got it.
The carboxyl group is different. It has the CO plus an OH group attached to the same carbon, so that becomes EaOH.
Ah, I see. So carboxyl is like a package deal. It's the carbonyl plus the hydroxyl.
Exactly. And that makes it a carboxylic acid. They are completely different functional groups with completely different chemistries.
Mhm.
Today, we're only talking about the carbonyls, aldehydes, and ketones. Got it. Carbonyl is just CO. Carboxyl adds the OH. I won't mix those up again. So, sticking with carbonyls, we have two main types, aldehydes and ketones. How do I tell them apart? Is there a trick?
It's all about position. Think of it like real estate location, location, location.
Okay, tell me the rules.
In aldehydes, the carbonyl group is always at the end of the carbon chain. The carbon is bonded to at least one hydrogen atom. It's on the edge.
Aldehyde is on the edge. Okay, so it's a terminal group.
Correct. Now, in ketones, the carbonyl group is never at the end. It's buried within the chain. It's sandwiched in the middle, bonded to two other carbon groups.
So ketone is in the middle, aldehyde is at the end. That's a clear distinction.
It's crucial for naming them systematically. If you get the position wrong, you get the IUPAC name wrong,
And you lose marks.
you lose marks.
We definitely don't want that. Now, earlier you mentioned that this CO bond acts like a magnet. I loved that image. Can we explore that analogy a bit more?
Yes, let's look at the primary analogy. Think of the carbonyl group like a standard bar magnet. Okay, a bar magnet has a north pole and a south pole, or a positive and negative end.
Exactly. The positive and negative end is what matters here. In our molecule, the carbon is the positive pole, and that oxygen is the negative pole.
And just like in physics, opposites attract.
100%. This polarity is the entire reason these molecules react. Because the carbon is positive, it attracts things that are
Negative, things that have extra electrons.
Yes. We call those nucleophiles. Nucleophile literally means nucleus loving. Since the nucleus is positive, nucleophiles love positive spots. So where will they go?
They'll be attracted to that positive carbon end of the magnet.
So the nucleophile attacks the carbon.
Correct. It attacks the carbon. I also read about the tug-of-war analogy. That really helps me visualize the strength difference.
That's a great way to think about it. Oxygen and carbon are pulling on the rope, which is the electrons. Oxygen is the heavyweight champion. It wins the tug-of-war, pulling the electron cloud over to its side. This leaves the carbon.
Electron poor or defenseless. Exactly. Defenseless and exposed, which makes it the perfect target for a chemical attack.
You know, sometimes I wonder, why do we need to go this deep? Why does this concept even exist in our syllabus? Can't we just memorize the reactions?
That's a fair question. But think about it this way. Without this concept of polarity, we simply cannot classify compounds or predict reactions. If you don't understand that the carbon is positive, you couldn't explain why a nucleophile attacks it. You'd just be memorizing random facts.
It would be memorization without logic.
Yeah.
And that is the hardest kind of studying.
Exactly. And historically, this is huge. Chemists in the 19th century, imagine being in a lab in the 1800s, they identified this CO bond as the key.
Right.
They realized that thousands of natural and synthetic compounds, from the perfumes they used to the explosives they were developing, all shared this specific bond behavior.
So this one bond connects perfumes and explosives. That's wild.
It is the common thread. It was the key to unlocking organic chemistry for them, and it is the key for us, too. Okay, to really lock this in, I want to try a mental exercise. For everyone listening, if you're in a safe place, maybe just close your eyes for a second. Let's run a mental movie. We need to see this molecule in 3D.
That's a great idea. Let's build it.
Okay, I want you to picture a carbon atom right in the center of your vision. It's holding 4 bonds. 2 of those bonds are pointing sideways, maybe slightly down, connecting to other groups.
Those are your R groups, the rest of the carbon chain.
Right. Now look up. Pointing straight up from the carbon are 2 bonds connecting to a big oxygen atom. That's your double bond. Now here is where we need to visualize the movement.
Visualize the electron cloud, specifically those pi electrons in the double bond. They aren't sitting still between the atoms. They're shifting. Watch them drift upward.
Like smoke rising.
Yes, like smoke drawn into a vacuum. They are moving toward the oxygen. Imagine the oxygen looking darker or denser because it's gathering all those negative electrons.
Okay, I see the oxygen getting dark and heavy.
Now look down at the carbon. It looks, well, pale. It's been stripped of its electron cover. It's exposed. It's glowing with a faint positive charge.
That pale carbon, that is the target.
That is the bullseye. Whenever you see a reaction in this unit, whether it's with HCN or Grignard reagent, just picture that pale positive carbon waiting for something to hit it.
That is a really strong image. Pale carbon, dark oxygen, the electrons shifting up. Okay, you can open your eyes now. That really helps explain the behavior.
Visualization is everything in organic chemistry.
So let's connect this mental movie back to the real world.
Right.
We started with the smell of nail polish remover and the biology lab.
Yes, let's talk about those observable phenomena. Let's start with formaldehyde.
Foraldehyde is HCHO, the simplest possible aldehyde.
Correct. Now, why does it smell so strongly? Why does it fill the room? It's because of that CO bond we just visualized. The bond makes the molecule highly polar. But because formaldehyde is very small, it doesn't stick to itself well enough to stay liquid.
Yeah.
It is volatile.
So it just wants to turn into a gas.
Exactly. It escapes into the air easily. And because it's polar, it interacts very strongly with the receptors in your nose. That's why you smell it immediately and why it feels so sharp.
It's practically attacking my nose receptors like a nucleophile.
In a way, yes.
And what about acetone, the nail polish remover?
Acetone is a ketone, formula CH3COCH3. Now, why do we use it to remove paint or polish? Why not just use water?
I always just assumed it was, strong stuff chemically.
It is strong, but specifically, it acts as a kind of universal solvent. Because of that CO polarity, it can dissolve other polar compounds, like the resins in nail paint.
So how does that work?
Think of the magnets again. The polarity of the acetone allows it to grab onto the paint molecules.
Yeah.
It pulls them away from your nail and into the liquid solution.
So manufacturers choose acetone specifically because that CO magnet is strong enough to rip the paint off.
Exactly. It's the direct technology application of this basic structural property.
That is actually really cool. It's chemistry in action on my fingernails. Now, here is where it gets tricky. And I think this is where a lot of students lose marks. You see a double bond in CO. You also see a double bond in CC, like in alkenes.
Yes, this is the danger zone.
You might think, hey, a double bond is a double bond. They must behave the same way. I mean, they look the same on paper, don't they?
But actually, no. That is a dangerous assumption. If you think they're the same, you will get the reaction mechanism wrong every single time.
Why? What's the difference?
Think back to our mental movie. In a carbon-carbon double bond, CC, like in alkenes, both atoms are the same. They're identical twins.
So the tug of war is a tie.
Exactly. The electrons are shared equally. The bond is nonpolar. So alkenes have a nice thick cloud of electrons sitting right in the middle. Because they have extra electrons, they attract electrophile species that are looking for electrons.
Okay, so alkenes attract electrophiles. They undergo electrophilic addition.
Correct. But in the carbonyl group, CSEO, as we've just seen, the bond is polar, the carbon is positive, so the carbon attracts
Nucleophiles.
nucleophiles.
That is a massive difference. One attracts electrophiles, the other attracts nucleophiles.
It is the difference between passing and failing a reaction mechanism question. Alkenes equal electrophilic addition, carbonyls equal nucleophilic addition.
Listeners, please write that down in red ink. CO attracts nucleophiles. CC attracts electrophiles. Don't let the double bond fool you.
It is the most common pitfall in Unit 8.
This brings us perfectly to our exam-safe clarity lines. We want to give you the specific sentences you need to keep in your head for the board exams.
Right. Let's go through the clarity checks from section B4. I'll say them slowly. Treat these as your revision notes.
Point number 1, identity.
The carbonyl group, CO, is a double bond between carbon and oxygen. Do not confuse it with the carboxyl group in COOH.
Remember, carboxyl has the OH attached, carbonyl does not. Point number 2 is naming.
In an aldehyde, the carbonyl carbon is at the end of the chain. It ends in -al. In a ketone, it is in the middle, bonded to two other carbons. It ends in 1.
Simple rule. Aldehyde at the edge, ketone in the center. Okay, point number 3, reactivity.
The CO bond is polar because oxygen is more electronegative. This makes the carbon the site for nucleophilic attack.
This is the Y line. If the exam asks, why do aldehydes react with nucleophiles? Well, this is your answer. And finally, the target.
Nucleophiles attack the carbon, not the oxygen.
That is the golden rule. Nucleophiles attack the carbon. Okay, we have covered a lot of ground today. Let's take a breath and recap what we've learned.
Sure. We started with the core idea. The carbonyl group is CaO. But it's not a happy marriage of equals, right? Oxygen is the greedy partner pulling electrons and making the bond polar.
We visualized the magnet analogy. Carbon is the positive pole, oxygen is the negative pole. We closed our eyes and saw the mental movie of the pale electron-poor carbon being left defenseless as the cloud shifted up.
We also looked at real-life examples. The sharp, room-filling smell of formaldehyde and the paint-dissolving power of acetone are both caused directly by this polarity.
And we locked in the positioning rule. Aldehydes are always at the end of the chain. Ketones are always sandwiched in the middle.
And remember the most important exam tip. Do not confuse CO reactivity with CaOC reactivity. Alkenes like electrophiles, carbonyls like nucleophiles.
Before we sign off, I just want to leave you with one final memory anchor to take into the exam hall. We call it the AK rule.
Ah, yes. Aldehyde equals end. Ketone equals middle.
And for the reactivity mechanism, what was that phrase?
Remember this. Oxygen pulls, carbon falls.
Oxygen pulls, carbon falls. Oxygen pulls the electrons. Carbon falls victim to the attack. That is brilliant.
If you can visualize that dipole, that separation of charge, whenever you see a CO bond, you will own the reactions coming up in the next topics. You won't be scared of Grignard reagents or alcohols because you'll know exactly where they're going to attack.
Absolutely. Understanding this structure is 50% of the battle won for this unit. Thank you so much for breaking it down with us today.
It was my pleasure. Keep visualizing those molecules.
And to our listener, thanks for tuning in. Next time you're in the chemistry lab, don't just pour the chemicals blindly. Look at the bottle. Visualize that dipole. Tell yourself, I know exactly what that CO bond is doing. It makes the practicals a lot more interesting. See you in the next deep dive.